Hi, this is Jian, a third-year doctoral student from the University of Tokyo. I will introduce our work. The name is SyntheWorld, a large-scale synthetic dataset for land cover mapping and building change detection. Okay, to begin with, the field of remote sensing image processing has advanced significantly with deep learning, finding extensive use in environmental monitoring, urban planning, and disaster mapping. So there are two key tasks, land cover mapping and building change detection. These two tasks are vital and forms the core of our research, which aims to improve the model performance in those areas. However, remote sensing image processing faces two major challenges. First, creating a high-resolution dataset that accurately represents the real world is extremely costly. For instance, for a high-resolution land cover mapping dataset, the annotation cost per image can be several dollars, even reaching over $10 sometimes. Additionally, annotating each image requires more than 2 hours of a professional's time. Okay, the second major challenge is that the remote sensing image is more easy to encounter some domain shift problems. So these problems arises due to various reasons, such as differences in sensors, geographic locations, or distance between the training and the testing datasets. So the figure in the lower right demonstrates how the model's performance is adversely affected when there is a domain gap compared to when there isn't. And it's evident that the model performs poorly in the presence of a domain gap. Synthetic datasets have emerged as a solution to those challenges due to their low cost and easily scalable diversity. So for a street view or indoor scenario, there are already many synthetic datasets with diverse and complex annotations. But for remote sensing scenario, there is still a lack of high-quality synthetic datasets with rich diversity. And the reason for this is that simulating high-resolution remote sensing images requires each pixel to represent a target within a 0.5 to 1 meter range. This means that creating a synthetic remote sensing scene demands a vast variety of 3D models, such as buildings and trees. From a CG perspective, this is much more challenging than simulating indoor scenario or a street view scenario. Motivated by this, we created our own large-scale synthetic remote sensing dataset, SyntheWorld. It includes 40,000 pairs of high-resolution RGB images, along with land cover and building change labels. Compared to existing datasets, our covers three tasks, and also unlike those based on video games synthetic dataset, our labels are auto-generated. Then we do not use manually designed 3D models. Instead, we build our 3D scenes using procedural modeling. Also, our dataset doesn't use any real-world textures. So the left figure below shows our dataset in feature space with different clusters representing different areas like the city urban with taller buildings, suburban areas with lower houses, or desert or plateau rural areas. The red figure shows a feature space visualization of different datasets. You can see that the deep blue dots representing SyntheWorld are closer to real-world remote sensing data than other synthetic datasets. All of those shows that SyntheWorld's rich diversity and high fidelity. Next, I will show how we build the SyntheWorld dataset using Blender and Python. First, we set up the sensor and the lighting parameters to mimic real-world distributions. And then for the layout of our synthetic thing, we had two methods. The first is grid-based, where we set the parameters like the grid numbers and sizes. The second method is procedural terrain-based, which created with different noise distributions. Then for objects like the rivers, roads, buildings, and trees in our zone, we use Blender's geometry nodes to set certain rows and generate these shapes procedurally. For example, for buildings, we decide the height distribution and the row shapes, then extrude the irregular flat to that specific mesh. Finally, for texture mapping, We use high-quality premobs created by teaching GPT-4 and feed them to the Stable Diffusion model to generate a wide range of diverse textures. In this slide, I'll dive into detail about our texture generation strategy. Initially, we used manually designed premobs to create textures, but with our GPT-guided premobs, they were quite simple, resulting in Stable Diffusion generated textures that lacked details and were hard to control. So we decided to feed GPT-4 with the techniques and details of using Stable Diffusion, and then show it some highly detailed premobs from the internet, known for producing high-quality images. Then we had GPT-4 created high-quality premobs based on 13 subjects, and we found that the texture generated by these three were much better in both diversity and detail than those from manually designed premobs. In this slide, I will show some examples from the SyntheWorld dataset. The top row shows RGB images annotations for land cover mapping task, where we mimic the category definition of the OpenEarthMap dataset. It's worth noting that in Blender, we can easily generate masks in different colors to use composite node. The bottom row is our built-in change detection examples. The process goes like this. After rendering an image, we change sensors and lighting settings and randomly remove some buildings. Then we render the modified image. By subtracting the masks of these two images, we can create annotations for the building changes. Now I will present some of our experimental results. Existing synthetic datasets only offer building labels, not multiple classes. So to showcase SyntheWorld's superiority, we conducted zero-shot building segmentation experiments on both existing datasets and SyntheWorld. The result shows that while there is still a gap compared to the real dataset OEM, SyntheWorld's performance significantly surpasses the existing synthetic datasets. Let's look at the result for land cover mapping experiments. It's quite clear that for two large-scale real-world remote sensing datasets, training with a mix of SyntheWorld and a small amount of real data yields better results than using real data alone. For the land cover mapping task, we also conducted some cross-domain experiments besides dataset level ones. We divided the OpenEarthMap dataset into 7 domains based on different continents. We then trained with a mix of each source domain and the SyntheWorld, testing on remaining 6 target domains. The heat map on the left-hand side shows that for most cross-domain experiments, SyntheWorld enhances the performance. However, there are a few source target pairs where SyntheWorld doesn't help, and may even reduce performance. To explain this, we introduce an RDR matrix to indicate when SyntheWorld is likely to be beneficial. This matrix is quite simple: the distance between target and the synthetic domain divided by the distance between source and target domains. The right-hand side correlation figure shows that the smaller the matrix, meaning the closer the target domain is to the synthetic domain, and the farther from the source domain, the more helpful SyntheWorld is. This aligns with our intuition. Then let me present our results for building change detection experiments. In Table 6, we tested 3 advanced change detection methods on 3 different datasets, with and without using SyntheWorld. The conclusion is clear: regardless of the model or datasets, using SyntheWorld always significantly improves the accuracy. Table 7 shows the result of one of these change detection methods on 3 datasets, using different proportions of training samples mixed with and without SyntheWorld. The conclusion remains the same: SyntheWorld consistently and significantly boosts the accuracy. Finally, I will show some visual results. So on the left-hand side, those results are for land cover mapping, and on the right-hand side, those are results for building change detection. We can see that training with a mix of SyntheWorld clearly improved the visual outcomes for both tasks. Okay, welcome to my poster session. The time is displayed on the screen. And if you have any questions, please feel free to contact me.